You think you know what an atom looks like. You've seen the pictures. A tiny nucleus in the center, like a ball. Electrons orbiting around it, like planets circling the sun. Clean, simple, easy to draw. That picture is in every textbook. Every science museum has a model hanging from the ceiling. Little balls on wires spinning in neat circles. But here's the problem. That picture is wrong. Not a little wrong, not close enough for government work wrong, completely, utterly, fundamentally wrong, in a way that should make you question everything else you think you learned in school. The atom is not a miniature solar system. Electrons are not little planets. And if you try to understand what's actually going on inside an atom using that picture, you're going to fail. You're going to get confused. You're going to ask questions that don't have answers because the questions themselves are based on a lie. So let me tell you what's really inside an atom. And I'm warning you now, you're not going to like it. Because what's actually there is so strange, so contrary to common sense, that your brain is going to fight me every step of the way. Let's start with the simplest atom, hydrogen. One proton, one electron. That's it. The atom everyone uses to explain things because it's supposed to be simple. You imagine the proton sitting in the middle, a little ball maybe 10 to the minus 15 meters across. And the electron is somewhere out there, maybe 10 to the minus 10 meters away, orbiting around it. First question, where exactly is the electron? You want to say, well, it's over there, on the left side of the atom right now, moving in a circle. Wrong. The electron is not over there. The electron doesn't have a definite position. Not because we can't measure it precisely. Not because our instruments aren't good enough. Because the electron itself doesn't have a definite position until you measure it. This is not philosophy. This is not interpretation. This is what the math says. This is what experiments confirm over and over and over again. The electron exists in a state we call a superposition. It's not here or there, it's here and there, simultaneously, in multiple places at once. The electron is smeared out in a cloud of probability around the nucleus. Now you're thinking, okay, fine, it's a cloud. So the electron is spread out like butter on toast, thinly distributed over a region of space. No, that's still wrong. The electron is not spread out. The electron is a point particle when you measure it. But before you measure it, it doesn't have a position. What's spread out is the probability of finding it in different locations. There's a function called the wave function that tells you where you're likely to find the electron if you look. In some places, the wave function is big, high probability. In other places, it's small, low probability. In some places, it's zero. You will never, ever find the electron there. But here's the thing that breaks your brain. Before you look, the electron isn't hiding in one of those high probability spots. It's not secretly over there and you just don't know where. It genuinely doesn't have a location. The wave function is the electron. That's all there is. Now let's talk about orbits, because this is where the solar system picture really falls apart. You imagine the electron going around the nucleus in a nice circular path, round and round like a racetrack. Maybe it's going fast, maybe it's going slow, but it's definitely going somewhere. Wrong again. First problem. If an electron were actually orbiting like that, it would be accelerating. Anything moving in a circle is accelerating, even if its speed is constant, because its direction is changing. And accelerating charged particles radiate energy. They emit light. That's basic electromagnetism. We can measure it. It happens. So if the electron were really orbiting, it would be constantly losing energy, radiating it away as light. And as it loses energy, the orbit would shrink. The electron would spiral inward, closer and closer to the nucleus, faster and faster, until crash, it hits the proton and the atom collapses. How long would this take? Do the calculation. It takes about 10 to the minus 11 seconds, 100 trillionth of a second. Every atom in the universe should collapse instantly. Obviously, that doesn't happen. Atoms are stable. They don't collapse. So the electron can't be orbiting. Okay, you say. So maybe it's not orbiting in a circle. Maybe it's just sitting there, stationary, held in place by the electric attraction to the nucleus. Also wrong. Because if the electron was sitting still, we would know both its position and its momentum exactly. Position, right there. Momentum, 0. And quantum mechanics says you can't know both of those things exactly at the same time. That's the Heisenberg uncertainty principle. It's not a limitation of measurement. It's a fundamental property of nature. If you try to pin down the electron's position, its momentum becomes uncertain. If you try to pin down its momentum, its position becomes uncertain. You can't have both. So the electron is not orbiting, and it's not sitting still. What's it doing? It's not doing anything. It just is. It exists as a wave function, a mathematical description of probabilities. And that wave function has certain allowed shapes and energies. We call these shapes orbitals. An orbital is not a path. It's not a trajectory. It's a region of space where the electron is likely to be found, described by the wave function. The simplest orbital, the ground state of hydrogen, is spherically symmetric. The probability cloud is highest right at the nucleus and falls off gradually as you move away. There's no orbit, no path, just a fuzzy cloud of might be here. Higher energy orbitals have stranger shapes. Some look like dumbbells. Some look like donuts. Some have multiple lobes. These aren't physical objects. They're probability distributions, maps of where you might find the electron if you look. And here's the really weird part. The electron doesn't gradually transition from one orbital to another. It doesn't slide smoothly from the ground state to an excited state. It jumps instantaneously. We call it a quantum leap. One moment the electron's wave function is in the shape of the lower orbital. The next moment it's in the shape of the higher orbital. There's no in-between, no smooth transition. It doesn't travel through the space separating the two orbitals. It just jumps. How? We don't know. The math describes it. The experiments confirm it. But there's no mechanism, no explanation for how the electron gets from here to there without passing through the middle. It just does. Now let's talk about what the electron actually is, because this is where things get really disturbing. You think of the electron as a little ball, a tiny sphere with some mass and some charge. Maybe it's very small, but it's still a thing, an object, a particle. Except when we do experiments, we find that the electron also behaves like a wave. It can interfere with itself. It can diffract around obstacles. It can spread out and recombine. All the things waves do. So which is it? Particle or wave? Neither. The electron is not a particle. It's not a wave. It's a quantum object. Something that doesn't have a classical analogy. Something that exhibits particle-like behavior in some experiments and wave-like behavior in others, but is fundamentally neither. When you're not looking at it, it's described by a wave function. That wave function evolves smoothly, spreading out, interfering with itself, doing all the things waves do. But when you measure the electron, when you actually detect it, you always find a localized particle, a dot on a screen, a click in a detector, never a smeared out wave. The act of measurement collapses the wave function. The spread out probability cloud instantly becomes a definite outcome. Here, not there. One spot, localized. And nobody knows how this happens. Nobody knows what counts as a measurement. Nobody knows where the wave function goes when it collapses. This is called the measurement problem, and it's been bothering physicists for nearly a century. There are interpretations, many worlds, pilot waves, objective collapse, but they're interpretations. The math works, the predictions match experiments, but we don't have a clear picture of what's actually happening. Let's make it worse. Let's add more electrons. Helium has 2 electrons. Lithium has 3. Carbon has 6. Iron has 26. These electrons are all orbiting, no wait, not orbiting. They're all existing simultaneously as wave functions around the nucleus. But here's the thing. The electrons are identical, absolutely, perfectly, fundamentally identical. There's no way to tell them apart. Not because they look the same, not because they're very similar, because they are the same. Electron number 1 and electron number 2 are not 2 different things that happen to have the same properties. They're the same thing appearing in 2 places. This has consequences. If you swap 2 electrons, the wave function of the entire system changes sign. It picks up a negative factor. This isn't a detail. This is fundamental. It's called the Pauli exclusion principle, and it's the reason matter is solid, the reason you don't fall through the floor, the reason atoms have structure and chemistry works and life is possible. No 2 electrons can occupy the same quantum state. If one electron is in a particular orbital with a particular spin, no other electron can be in that exact same state. They have to stack up, filling different orbitals, building the structure we call the periodic table. Without this rule, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. There would be no complexity, no molecules, no chemistry, no you. But why? Why does swapping identical particles change the sign of the wave function? We don't know. It's just the rule we discovered. The math works. The experiments agree, but there's no deeper explanation. Now let's talk about the nucleus, because you probably think that part is simple. A bunch of protons and neutrons packed together. Little balls stuck to each other. Wrong again. Protons and neutrons are not fundamental. They're made of quarks. 3 quarks each. Up quarks, down quarks, held together by the strong nuclear force, mediated by particles called gluons. But the quarks don't sit still inside the proton. They're quantum fields.